For our third technique, this is one of the most dreaded things in pre-calculus algebra for some reason. Mathematicians love it. It's very elegant and it works out very nicely. But non-mathematicians, I guess, just don't understand it for some reason. But it may be helpful if we complete the square. So we are going to turn something into a perfect square. And that hopefully would help us to integrate. Just a quick example of completing the square outside of an integration problem. If I wanted to complete the square on x squared minus 6x plus 2. Complete the square means get that written as a perfect square, as a sum or difference of squares. Right now it is not. It doesn't even factor. The problem is this constant. We don't have any control over the x's, but we could possibly add or subtract from this polynomial and kind of fudge that constant. So that's where we're going to work with. So we're going to think of this as x squared minus 6x. We really have no control over those. But there is some other constant that would make this a perfect square. And I would rather that get grouped with my x squared minus 6x. And I'm going to move my little plus 2 to the side because that's really not helping us. We can't get rid of it completely, but I'm going to move it off to the side because it's not helping us. Now, in order to not violate any laws of math, in order for us to add in this new constant that's going to make those first three terms a perfect square, I'm technically also going to have to subtract that same constant off so that the net result is 0. So I'm really not changing the value of my polynomial, I'm just changing the way that it looks. So those two blanks are going to be the exact same number. So the way that we figure out what exactly is going to make this a perfect square is we take that linear coefficient of -6 and we divide it by 2, and then we square it. So -6 divided by 2 is -3, and then -3 squared is 9. If I had a 9 on that first blank line, I would have a perfect square in my first three terms. So that's what we're going to do. We're going to add a 9 there. And in order to not change the value of this polynomial, I'm also going to have to subtract 9. But I'm going to put it in a different spot. I'm going to move it to the end. So this is going to turn into x squared minus 6x plus 9. I like those three terms together because they're going to make a perfect square. But then the +2 and -9, I can put them together afterwards. They're going to make a -7. So now this first piece is a perfect square. It will factor to one value squared. Excuse me, it is not a plus. It is a minus. So x squared minus 6x plus 9 is going to factor to x minus 3 squared. Now I have a perfect square. The pieces that involve my variable x are collapsed down into a perfect square piece. And notice now that my original problem started off with 2 variable terms, and I've been able to now write it with just 1 variable term. That is going to be very helpful, especially with integration, and also because that variable term is now linear. That's going to help a lot with U substitution. So let's look at one example real quick with an integral where we might have to do this. We're going to try to integrate, let's say, 3 over x squared minus 2x plus 10. The first two techniques that we saw in this chapter were to split apart the numerator. Both of them involved rational functions, and this one is as well. We can't split apart our numerator, though it only has one term, and we can never split apart our denominator. So we're not going to split apart the numerator. That's not feasible. We also are not going to do any polynomial long division, because on the inside, our dividend here is going to be 3. So the very first division I'm going to try to do is ask, how many times does x squared go into 3? And it doesn't. So there's no division we can do. It's a proper fraction, meaning the exponent in the bottom is bigger than the exponent in the top. So it's already proper. We can't do any polynomial division. U substitution is not going to work, because if we let u equal to our denominator, u would be x squared minus 2x plus 10. And then the du would be 2x minus 2. So the du still has x's in it, which means when we pull it back in, we'll have an integral with a mixture of u's and x's. There's no other x's in this problem to get rid of. So I'm going to complete the square, and I'm going to come outside of my integration problem here to do it. Sometimes if you try to do it inside the integration problem, it gets really messy. I'm going to complete the square in that denominator. X squared minus 2x plus 10. Now, we really have no control over those variable terms, but we could put a different constant there that could make those variable terms turn into a perfect square. And I'm allowed to add that new constant as long as I also subtract it somewhere else. And I can't get rid of my plus 10. I've still got my plus 10 there. I've just kind of moved it off to the side because I know it's not the correct number I need for my perfect square. So remember what we did before. We took that linear coefficient and divided it by 2 and then squared. So that's going to give me negative 1 squared, which is 1. So the magic number that's going to make this thing a perfect square is 1. So now I've got x squared minus 2x plus 1. All of that stuff is going to factor. And then I'm going to put my constants together. My plus 10 and my minus 1 makes a plus 9. And then finally, this is going to factor to x minus 1 squared plus 9. And I'm going to replace my denominator here with this new expression. It's an equivalent expression, except we have it now written with a perfect square. So it would be the same thing to ask what is the antiderivative of 3 over x minus 1 squared plus 9. This is another special inverse trig formula that you may remember from Calc 1, you may not. But this one turns into arctangent. So again, back in the end of chapter 3, we have that the derivative of tan inverse x equals 1 over 1 plus x squared. We don't have a 1 plus x squared, though. The 3 in the top is not a big deal. We can pull it out front as a coefficient. So I'm just going to show you the more general integration formula. If we're asked to find the antiderivative of 1 over u squared plus a squared du. So the u piece is the variable piece. It doesn't have to be just a plain old x. It could be a function of x. This is going to turn into 1 over a arctan of u over a plus c. Now, I kind of go back and forth between tan inverse and arctan. They're really the same thing, and it's up to you how you write it. It doesn't matter which one you use. So this is the more usable format. We're not just going to have a plain old x in our angle. We're actually going to have a function of x on top and a constant on the bottom, and that is because we've got a function of x being squared as in the variable part, and we also have a squared piece here. If a squared is equal to 9, that means the a that we're going to put in our answer is 3. And then if u squared is x minus 1 squared, that means u equals x minus 1 and du equals dx. So it's a straight swap. There's no extra coefficients coming back in when we do that u substitution, because du equals dx. So our answer ends up as 3 from the numerator times 1 over a, so I've got 1 over 3 arctan of u over a, so x minus 1 over 3. And these guys are going to cancel, so we really just have arctan of x minus 1 over 3 plus c, because we're not evaluating. Like I said earlier with the arc sign, don't get caught up with knowing that arctan formula. In section 7.4, we're going to talk a lot more about that, and you'll be able to figure out that that antiderivative is arctan without memorizing that formula. So the last little algebra or trigonometry trick we're going to do is we are going to use Pythagorean conjugates. And that's an awful big term, huh? So we'll walk through exactly what that means, and we'll look at one. So Pythagorean, these problems are going to have trig in them. So Pythagorean, there are a list of Pythagorean identities in trigonometry. And those identities say that sine squared plus cosine squared equals 1. Also that tan squared plus 1 equals secant squared. And then 1 plus cotan squared equals cosecant squared. Now in all of these, we've got sums of squares. And you cannot factor a sum of squares. So what we're going to do is we're going to kind of reorganize some terms so that this looks like a difference of squares. So I could say that sine squared equals 1 minus cosine squared. And let me actually just work with this one at a time. So I'm going to erase my arrows here. Now 1 minus cosine squared is a difference of squares, which means I could factor it into one of each with a plus and a minus. So 1 minus cosine squared will factor into 1 minus cosine x and 1 plus cosine x. So everything I just did here, when we multiply by a Pythagorean conjugate, we're going to be doing that backwards. So conjugate might be a kind of familiar term from algebra class as well. Conjugate means I'm using the exact same expression. The only difference is I changed the sign. So notice that one of them has a plus and one has a minus. So the Pythagorean conjugate is the exact same expression, but with the opposite operation between. So if we were to FOIL these out, we would get a difference of squares that matches up. Instead of having 2 terms, we could convert it just into 1 term. So this is a way for us to take some integration problems that might look kind of tricky and hopefully take them from being just a sum or a difference here and turning them into a difference of squares, and then replacing them out completely with just a single trigonometric function, which will certainly be much easier to integrate rather than having 2 terms to integrate. And this is true for all of these Pythagorean identities that I have written. We could turn any of these into subtraction problems by pulling one of the terms from the left over to the right. And then once it's a subtraction problem, we would separate it into our two binomials where we've got one of each, except one is a plus and one is a minus. And there we have our Pythagorean conjugates. So let me show you an example of a integration problem where we might want to use this. Suppose we were asked to integrate 1 over 1 minus cosine x. It is a quotient, so you might start to think u substitution, except our u is going to have a cosine in it, which means our du is going to have a sine in it. And nowhere else in this integrand do I have a sine function, so it's not going to work. But this guy almost looks like our Pythagorean identity up here. If that just had a square on it, that just said 1 minus cosine squared, then this would be a lot easier, because then I could replace it with sine squared, and then I could move it to the top as cosecant squared. It would be a whole lot easier. So we can make that say 1 minus cosine squared by multiplying by the Pythagorean conjugate. If I were to multiply by 1 plus cosine x, we just showed up here that 1 minus cosine x times 1 plus cosine x is 1 minus cosine squared. And I'm allowed to do that to my denominator as long as I do the exact same thing to my numerator. So then this turns into 1 plus cosine x over 1 minus cosine x squared. And 1 minus cosine squared is equivalent to sine squared. So we're able to take something that has two terms and replace it with one term. Anytime we can reduce the number of terms we're dealing with, it's always going to be easier. And now we're going to go back to the very first technique we talked about, and we are going to split apart this numerator. So now I've got 1 over sine squared plus cosine over sine squared. Both of these we could just use some basic trig identities to simplify. This is cosecant squared plus, well, cosine over one of those sines is going to be cotangent. And then we have an extra sign in the bottom, so it's times cosecant. Both of these have straightforward antiderivatives. The antiderivative for cosecant squared is negative cotan. And the antiderivative for cotangent cosecant is negative cosecant. So all we have to do, if we recognize that we have 1 plus a trig function, 1 minus trig function, or vice versa, the 1 doesn't necessarily have to be in the front, but we've got a trig function plus or minus 1. If we could get that trig function to be squared, then it will match one of the sides of our Pythagorean identity, and we could replace those two terms with just a single term and then simplify much easier from there.